Today we are going to study light waves. What is light? Light has a dual nature. It sometimes can behave like particle, and it also behaves in a wave form. Today we are going to study the wave behavior of light, not the particle. We have seen wave behavior in case of sound, motion of strings. Light waves behave very similar to that. And a general equation of a light wave is this equation you have seen umpteen number of times. Except that we take E as electrical field, right? Next thing is Highgens principle. What it says is, suppose you have a light source, it starts emitting waves all around it in a spherical fashion. And when it hits any other surface, the particles of this surface starts acting as a secondary source, meaning thereby each of these sources will start emitting their own waves. And for example, if this wave hits another surface, then again this will act as a secondary source, and this process goes on. So this is in very brief the Highgens principle. What it says is, when a wave front, what is a wave front? Wave front is a path where all the particles are in the same phase. For example, this. All the particles here on the surface are in same phase. When a wave front hits any surface, it creates secondary wavelets which behave exactly like primary source. And when these wavelets hits another surface, another series of wavelets will be produced. So the process goes on. This is in a nutshell the Highgens principle. Now we will explain this principle with the help of process of diffraction. Let us say we have two media. Maybe this is air, this is glass, not necessarily, just for the sake of argument. This is medium 1, this is medium 2. An incident light falls on this media separation. This is a wavefront. This AB is a wavefront coming like this, parallelly. When it hits at this point, the wavefronts cannot travel with the same velocity. What happens is its velocity changes because the media has changed. And we know that light travels faster in rarer medium and it travels slower in denser medium. So if we say the velocity here is v1, velocity here is v2, then velocity v2 is less than velocity v1. So let's say in some time t, this wavefront reaches here, and this distance is AE distance is velocity times time taken, right? Now within the same time, the wavefront here has reached point C. So we can say BC is equal to V1T, right? Okay. Now if this is I, this is also I geometrically. So geometrically, if we see, what is sine of I? Sine of I is perpendicular, which is BC by this hypotenuse, which is AC. And BC we have seen it is velocity times T. AC, let's keep AC as it is. Now we take sine R. Sine R is what? This distance, which is AE, divided by hypotenuse, which is AC. This is equal to, and AE we have seen is this much. Now if we divide sine I by sine R, what you get is this cancels away, and what you get is V1 by V2. So what it essentially means is then that during refraction, sine I by sine R is equal to ratio of the velocity in respective medium. Okay. Now we also know refractive index is given as velocity of C in vacuum velocity in that media. Right? So mu1 of media 1 is C, which remains constant, velocity v1, whereas mu2 is C times velocity of light in media 2. And again, if we see sine I by sine R, we take this argument is what? Mu2 by mu1, or mu1 sine I is equal to mu2 sine R. This is our Snell's law. Okay. Now let's see how does the wavefront behave in case of reflection of light. Let's take this wavefront AB coming parallelly. When it hits point A, it immediately returns back. But point B takes some time to reach C. And by the time point B reaches C, point A reaches E. So a new wavefront is created. This is the new wavefront that is created. By the time this point A reaches E, B has already reached C, and they start to move like this as a reflected wavefront. This is reflected wavefront. And we can clearly see that triangle EAC is congruent to triangle BAC, which is EAC. This is EAC, this one, and BAC is BAC. They're congruent to each other, meaning thereby this angle is same as this angle. It means angle I is equal to angle R, and we say angle of incidence is equal to angle of reflection. This is basic law of reflections. The nature of light as wave is beautifully explained in an experiment called Yanks double slit experiment. I will explain you what it is. You have a light source and this light falls on two small slits which are made very narrow. This distance is very, very narrow. And when this the same source falls on two slits, the rays from each of them interfere with each other and forms a fringe pattern. What is a fringe? A fringe is a band of dark lines. For example, we call it as a dark fringe. In this area, which is brighter, we call as bright fringe. Okay. Now, how is the experiment set up? It is like this. This is our two slits. These two slits, which was shown here as this one and this one. And they are obviously illuminated by a coherent source, which goes to both these slits. And a screen is placed at some distance d from the slits. Now, the distance between S1 and S2 is d, small d. Now let's see how the rays travel. This ray travels from S1 to P, let's say, and takes this path. There's another ray which travels from slit S2, reaching point P. Is one longer than the other? Yes, the bottom one is longer than the other, because if we draw a perpendicular here, from here to here, or from here to here, both the paths are equal. But this much part is extra. This much part is extra. So this we call as delta x. Okay. Now, if we write our equations for waves, let us say one wave from slit 1, let us say this is from slit 1. The electric field is defined as okay. And from E2 is defined as E sine now x was the case, this was from slit 2. This was the x was the distance in first case, and in second case there's an extra distance delta x coming in. Now if we take the resultant of these two waves, it can be written as this is the phase difference between the resultant and the wave E01. So this is the between the E1 and resultant. Then if we evaluate the amplitude of the final wave is given as now this delta is the difference between two waves, E1 and E2. This is the phase difference between E1 and E2. Now this equation must be looking very familiar to you, isn't it? Where have we seen it before? We have seen it before when we were doing vectors. And what it basically says that if you have two vectors, E01, E02, which are separated by an angle delta, then the resultant is given by this formula, where delta is the phase angle between the two. And what is eta? Eta is the angle between resultant and E0. This is eta. And we can also evaluate this angle, which is given as tan eta is written as this. Also we have seen earlier when we were doing vectors to find out the resultant vector and the angle between resultant and one of these vectors. Now for constructive interference, our delta should be phase angle. If two vectors are added together, how best they will be added to give maximum resultant would be when delta is 2n pi. That means if this is vector 1, this is the another vector completely lies over the other one, meaning thereby there is no phase difference between the two, or if there is a phase difference, this is 2n pi. 2n pi is not a phase. A phase difference of 2n pi is same as saying that there is no phase difference, because it's a multiple of 2 pi. 2 pi is 360 degrees. So this is the condition for constructive interference. And for destructive interference, if these two are to be destructive interfering, then what should happen is they should be opposite to each other. And when will this happen? This happens when the phase difference between the two is 180 degrees or pi. So what we do for generalities, we take this we take 2n and this is for this 2n will give you a complete cycle, so it will not create any phase difference, this one. But when you add pi to it, this will create phase difference of pi between the two waves, which will cause destructive interference and this will give you a dark fringe. Just to repeat, for bright fringe, delta is 2n pi is equal to now we can write this delta in terms of path difference also. If we travel lambda distance, for example, traveling lambda distance means traveling one full wave. When we travel one full wave, we cover an angle of 2 pi. So if we travel lambda distance, in terms of angle, we travel 2 pi. And if there is a delta x path difference, this is the phase difference between the two paths. So when we take 2 pi then what happens is our delta x is lambda. This is again is logical because n lambda means integral multiple of lambdas. Whether you cover this was 1 lambda. Now whether you cover one wave or you cover two waves, suppose this was A in first case to B and C, we will see that phase difference between A and B is 0, or B is in phase with A, and if we travel another cycle, then point C will be in phase with B, which means that if we travel multiples of lambda, the phase difference will be actually 0, and this will be condition for constructive interference, resulting in bright fringe. And what will be the condition for dark fringe? For dark fringe, delta is equal to this is in terms of pi, and in terms of path difference, same equation as before, delta x, which implies delta x is equal to this phase difference of half lambda will cause two waves to be opposite to each other, resulting in destructive interference, or it will result in dark fringe. Now let us calculate the intensity of the resultant wave. We know the amplitudes are related like this. This is the amplitude of the final resultant wave. E0 was one of the original waves. E02 was the second original wave. This is the phase difference between E1 and E2. Now, in case E01 amplitude is same as E02 amplitude, which is the case in case of a double slit experiment, then our resultant wave becomes 2 times E01 square. This and this gets added, gives 1 plus this and this will become 2E01 square cos delta. So this we have taken out, and this is cos delta. We know intensity is proportional to square of amplitude. So we can also write this is the final intensity. This will represent the initial intensity. This is also written as, we add these two trigonometrically, and it results into Now, if delta, which is the phase difference between E1 and E2, if suppose it happens to be 0, then what will happen? This will simply become 4E0, 4I0. I will become 4I0 if delta is 0, or added to it multiples of 2 pi's. Now, looking at this diagram, we can see theta is a very small angle. So for small angles, theta is same as sine theta, and sine theta can be defined as delta x by small d. If I draw this small portion of the, if I redraw this area or magnify it, something like this. You have this perpendicular. This is S1. This is S2. This is D, sorry. And this portion is our delta x. So sine theta can be defined as, this is theta. Sine theta will be defined as perpendicular upon this hypotenuse, which is delta x by d. And it is also defined as, this is also theta. This is also theta. So we can say this theta is also equal to this y divided by d. Yeah. Or we can say that delta x is equal to y d by d. We know that this is the distance between slits. This is the distance between slits and screen. Now let's try to calculate fringe width. What is a fringe width? We've already seen that we get fringes like this. There's a dark fringe. Then there is a series of dark fringes. It will happen symmetrically about the center line. So this is a dark fringe, this is a dark fringe, this is a dark fringe. The distance between two successive dark fringes or two successive bright fringes, whichever one you take, is called fringe width. This is our fringe width, and this is also, this distance is also our fringe width. Both will be same. So fringe width is the distance between two successive dark or bright fringes, whichever one you take. For bright fringe, our delta x should be equal to n by multiple of lambda multiple of lambdas, and delta x we have already seen is defined as, or y can be written as dn lambda by small d, which implies that our y is equal to, can be, if we put n as 0, this will be 0, then it will be plus minus. Why plus minus? Because we have seen our fringes are symmetric about the center line. If you get a dark fringe at this height, you will get another similar dark fringe at this height. So this side will be plus y, this side will be minus y. That is why we take plus minus. The second one will be and so on and so forth. Now, at y is equal to 0 means what? We are at the center line. We are here, this place. At center line, y is 0. Here what we get is a bright fringe, is a condition for bright fringe. So the central portion is bright, right? Now what happens for dark fringe? Our delta x should be integral multiple of lambda plus half. So this makes it a difference of half lambda over and above integral multiple of lambdas. This is also equal to or y is equal to lambda. And we can see y is equal to or plus minus 3 by 2 or 5 by 2 d lambda by small d, and so on and so forth. Now, if you examine y for bright fringes, what is the difference between these two? What is the difference between these two? And so on and so forth. Now, in case of dark fringes, what is the difference between two successive dark fringes? Is and if we take difference between these two, what is the difference in y? Is again. So what we see is, and what is this? This and this? This was distance between two successive bright fringes. And similarly, this is the distance between two successive dark fringe. So can we say that our fringe width, if we define as W, is first of all, quantitatively it is d lambda by d, and it is also can be defined as distance between two successive dark or bright fringes. The only condition is that they should be successive, one after the other. Velocity of light being different in different media, yes. So let's see the details of velocity of light. Suppose this is air, this is glass, and incidence rays comes like this, goes like this. Is the velocity of light here and here different? Yes, they are different. If we take velocity of light here as v1 and here as v2, then since glass is denser than air in terms of optics, so in glass the velocity is lesser than what it is in air. So we can say v2 is less than v1. Also implies that lambda 2 going to be less than lambda 1 because frequency never changes. Frequency in both the media will remain same. If frequency remains same and delta changes, so obviously the velocity will change. We can say delta 1 is velocity of light in media 1 divided by frequency. Since frequency doesn't change, we don't designate it any differently. Lambda 2 will be velocity. We substitute this from this expression. V2 lambda 1 we have already seen this expression earlier. This is called mu of media 2 with respect to media 1. V1 by V2 is mu of 2 with respect to mu of media 1. Okay. Or we can also say V1 by V2 is equal to another form of writing. Mu of media 2 with respect to media 1. Also, if we take one of the media as vacuum, then we can say velocity of light in vacuum divided by velocity of light in glass mu of glass with respect to vacuum. Next, we will study interference from thin films. Let us say this is our thin film of thickness D, and incident light falls on it. Obviously, it will bend. Again, it will spread out like this. Okay. But we have seen it is not necessary that all the light will get transmitted, get refracted. Some of it will get reflected also at the same angle. Right? Now, this ray which was refracted may not be fully going to another media. Some of it may reflect back. And again, same thing may happen. Again, there is another reflection. And then it comes out. Here also, what may happen? This, this ray, after hitting this point, some of it may go out and some of it may reflect back. And this we capture through converging lens. This point is P dash. This is P. And then this is B, D, this is A, C. Then what we see is path BP is same as path DP, but BC DP travels an extra distance of what it says is, if we say BP, the path of ray going from this point to this point and to this point is this much, whereas this path is same. This path is same as this path, but if the ray takes this route, then it has to travel this much extra, yeah, which is BC plus CD. BC is this much, CD is this much. All right. So the path difference created is two mu d. Now, 2 mu d means BC we approximated to D, and CD also we approximated to D. So these two differences 2D. But we don't take this as this path difference is in this media. And we have seen velocity of sound, velocity of light in different medias are different. So what we do is to equalize them, we call something, a term is used called optical distance. What is an optical distance? It is, you can take a geometrical distance, difference of geometrical distance multiplied by the refractive index of this media. Using this, we can then now compare, take differences, addition, comparison of path differences from any media. Otherwise, a path difference here cannot be compared as with the path difference here, because mu here is mu1 and here it is mu2. So you cannot compare the two. So to generalize it, what we do is, instead of taking geometrical distance, we take optical distance. This is the optical distance. For BP and BC DP. Basically this and this plus this plus this. Difference between the two, if this ray and this array taking this path and array taking this path is supposed to do a constructive interference, then this path difference should be multiple of lambda, or path difference in terms of angle should be in terms of angle is 2n pi, because when the difference is a multiple of 2 pi's, it doesn't matter what trigonometric function you take. After 2 pi, you will get the same, the trigonometric function will repeat. And we also know phase difference is also given as, we know if the phase difference is a lambda, that means there is a 2 pi difference, or into path difference is 2 mu d. So the phase difference and path difference is defined like this. For BP and BCDP to be destructive, what should happen is, this should be equal to integral multiple of lambda, you add half lambda. So half lambda will make two waves. One will go like this, one will go like this, and eventually they will cancel out each other. But you phase angle will be we have seen, so long as when a wave travels 2 pi distance, it comes back to its original starting position. Suppose it started from here. When it comes to B, having traveled 2 pi angle, phase becomes same. Now to make, so next it will go like this. If there is another wave which is supposed to oppose it, then it should start from here. Starting from here means a phase difference of between this and this delta should be pi, like this. Here n is equal to 1, 2, 3, and so on. In case of reflection, these criteria is reversed. Meaning thereby, if you are getting constructive interference in refracted phase, it will mean destructive destruction in reflection. So if you have constructive in refraction, this would mean a destruction in reflection, and conversely, if you have destructive condition in refraction, this will mean constructive condition in reflection. So what it means is, if you see brightness in refraction, you will get darkness in reflected light, and conversely. Next topic is Fresnel biprism. What is a Fresnel biprism? It is basically a combination of two thin prisms, one like this and another one like this, with very small base angle. This base angles are very small. When they are in this fashion, and if you have a source of light S here, what happens is the ray takes place this path on the upper side. At the bottom side, they take this path, and you get, this is the screen. Now, when you see this ray diagram, this is the real ray, these are real rays. But if you extend them back, this seems to be coming from here and here. So it appears that source S1 and S2 are behave like virtual sources. because geometrically everything is between S1 and S2 are identical. So the sources are also coherent. There is no reason to believe that there will be phase difference between S1 and S2. Now, if you forget about this portion, just forget about this portion, isn't it equivalent to Yanks double slit experiment? What did we have there? Two sources, this and this, separated by a distance d. Yes. And a screen, this screen is placed at a distance d. Yes, looks exactly like that. It is, in fact, it will exactly behave like Young's double slit experiment without any change in treatment.